Okay, so our next one is a slightly more realistic. That's the finite square potential well. Okay. So this problem will have two classes of solutions. So let me just first draw the potential. So the potential looks like this. So we have V of x, and then we have this is the x-axis, and this is V naught. This is okay. So maybe we should have the V naught here. This is V naught. Okay. And similarly, let's have three regions: region 1, region 2, and region 3. But there are three classes of solutions. One is when the energy is positive and greater than V naught. Okay, when the energy is, the other one is the energy is less than some value than V naught. Okay, and there's also the critical one in between. But E is greater than V naught, the total energy, and the other one is E is less than V naught. For E greater than V naught, we'll have some sort of wavy solution, although its wavelength will vary depending on whether you are in this region or this region or this region, and that's kind of easy to work out. But for this guy, we are going to have some discrete bound states. Okay, so here we are going to look for the bound state solutions. We look for the bound states. Okay, and let's call this L by 2, and this is minus L by 2, and this is the origin. Okay, any questions about the setup of the system? Okay, all right, so so region 1 and 3 are easy to solve, so let's do that first. So in regions 1 and 3, where psi is of the form of E, some constant A times E to the power minus K1 of X plus B E to the power plus K1 of X. By K1, I mean this thing. K1 is 2m V naught by E square root divided by H bar. Okay. Now, you see that one thing we can do is that, say in region 3, in this region, if we allow, say, B to be non-zero, then we will be in problem because we will be in trouble. Because if I take K to be very, very large, here K1 is positive, then this thing is going to blow up, right? If it blows up, then the overwhelming possibility would be for the particle to be found far away in a region where the particle has imaginary, velocity. Okay, so we expect, or negative kinetic energy, right? So we expect that the particle will not go very far into this region if it was initially confined here. So that means that in region 3, we are going to set B to 0. Okay? So in, say, region 3, we set B to 0. Similarly, in region 1, we set A to 0. Okay? So in region 3, A doesn't have to be 0. And that means that in region 3, the wave function can be exponentially damped or decaying. So what this is meaning is that there is a possibility that the particle is going to be found, outside the box. Okay, so and similarly for region 1. Okay, and another reason why we cannot have B in region 3 to be non-zero is because then this wave function is not going to be a normalizable wave function, right? And that's not going to be physical. Okay. All right. Any questions so far?
What are those green lines for?
That is going to be the wave function, the exponentially damped wave function in region 3.
Oh, I see.
And the exponentially damped wave function in region 1.
I see. Yeah. Okay.
Okay. It's a very good question. Yeah. Now, what about in this region? In this region, there is no, there is no potential energy, right? So we will have a sine wave or a cosine wave, right? So, our intuition from the previous exercise is that the lowest energy state will be 1, which is a cosine wave. Now, see that we have a finite potential well, right? So we have a finite potential well. So this means that psi double prime, this has a finite discontinuity, right? So this means that psi prime is continuous. Right? And that means that psi is not only continuous, but it's also differentiable, right? So this means that we can have a potential energy, we can have a wave function inside, but that wave function will look something like this. It'll smoothly, let me use a different color. It will smoothly go and join with the wave function outside, okay? So there is no discontinuity here. Or not only does discontinuity, it's actually smooth, it's differentiable, right? Now, so, okay. Any questions?
So I think I missed it, but what would happen if E is equals to V naught?
If E is equal to V naught, that's a critical condition. That would be the limit of what we are going to be discussing. Okay.
Ah,
Yeah,
okay.
That's a good question. I haven't really thought very carefully about it. That's going to be the boundary between the two. Yeah, you can pretty much tune that. I think you can tune U naught. That's a very good question. Let's come back to that. Down below, we'll let's think about that.
Okay, sir.
Okay. So, so suppose that we analytically continue this wave function, then what we can say is that fictitiously, the wave function that we have, that I am like outlining in a very light blue color. I don't know if you can see it. Like, let me just do this. Can you see it? I hope everyone,
Yes, I can see it.
Yeah. So, this wave function, the blue wave function, would have been a wave function, the ground state wave function for a particle in a box whose size, let's call the size of the particle in a box to be L prime. So L prime is obviously going to be greater than L, right? Which is the real size of the finite box that we have. But you see that for the particle in a box, we found that the energy is proportional to 1 over L squared, right? One over L squared. So from this, we can say that, okay, because you see the energy, what I want to say is that, right. So what I want to say is that if you compare the ground state energy of a particle in a finite dimensional well, that's going to be lower than the ground state energy of a particle in an infinite well of the same size, right? Does that make sense?
Yes, sir.
Okay. Yeah,
Isn't
because
the infinite well a little longer? And I'm confused.
yeah, I think I didn't do the best job in explaining this. What I should have, yes, the infinite well is a bit longer. You're right. Yes. And because it's longer, if you had an infinite well, which had the same size as the finite well, its energy, its energy would be higher. Right? Because L would be smaller, L would be smaller, and therefore E would be higher, right? Whereas, this guy, the finite well, its energy is actually is equivalent to the energy of an infinite well, which is slightly larger. Okay?
Yeah, makes sense to me.
Okay. So let's, okay. So